We are now going to go through the actual approach of getting fields from an extended charged object. This is going to really just be describing the general approach. In the next video, we'll look at a specific example. So hopefully you've already feel like you understand the earlier content of how we can find the field from multiple point sources. So we need to extend that idea now. So before, what we said was that your total electric field, or your net electric field at one location in space, is given by the sum of all of the individual electric fields at that point in space. So for instance, if we have 3 charged particles, then we would need to add up the electric fields from each of those 3 charged particles to get the total electric field at that point. So now, instead, what we're going to do is we're going to take that sum and turn it into an integral. Why? Because we no longer have a finite amount of point charges. If we think about an object like a wire or a rod, we can think about breaking it into little tiny pieces where each one is a point charge. But the question you might ask then, here I happen to be circling each of the charges, but you could imagine that if I used just smaller circles, there would be more of them. So we no longer have a finite number to add up, but we can make our our little bit of charge here smaller and smaller until we reach an integral. So what that means is that instead of thinking about just charge, we would be thinking about the integral of little bits of charge, where each dq is just some little section of my object. Now, when we actually want to go and integrate that, we don't actually know how much this charge is, but we know in the case of a wire what its linear charge density is. So now remember that we said that delta Q, so the amount of charge given in a little area, is going to be equal to our linear charge density times your delta L. Where in this case, again, this is the tiny amount of charge, this is the length. So once we go to the integral, this delta L is just going to become my dx for doing the integral. So your lambda stays there, and now we integrate over the entire length of the object. So that's how you can think about this. Now, mathematically, we're going to do it a little bit differently. We don't necessarily start with this, so I will talk about that process, but you should think about the fact that instead of doing a sum, we're going to do an integral, and we're not actually doing anything that different other than thinking about each one of these as a point charge and realizing that we do actually need to do an integral to really get back to our total amount of charge. So what is our strategy overall for doing this? So first, whatever object you're given, it might be a real-world object, you need to model it as a simple shape. And we actually started the chapter covering what some of those simple shapes are. So make sure you have a sense of what those can be, and in this chapter we'll go through more or less those shapes. But if you're looking at something and you think, well, it should probably be a cylinder with a cube coming out of the side of it, well, you don't actually know how to calculate that. I don't know how to calculate that. So pick something simple, but not too simple. And make sure you do describe this as part of your simplification and modeling. Now, the next step as always is going to be visualization, creating that representation. And this is typically going to have 2 or 3 parts to it. So first, we're just going to have what I would call the normal picture. That should include a coordinate system, and you want to identify the point at which you're technically doing your calculation. Now, in some cases, you might be asked to find it at a specific point, but in other times, this is a generalized point that just allows yourself to plug in some variables. Now, what you might do in the same picture, though I would encourage you to consider drawing a second picture to make it more clear, or make sure this first picture is really big, is to start dividing your object into small pieces of charge delta Q. And again, the big takeaway here is you want to use shapes for which you already know the electric field. Now, what might that look like? Initially, that's going to be point charges. So frequently, the shape is just going to be a dot. Imagine a bunch of dots where those are your point charges and they make a shape. Now that will initially give us a line. But what you might imagine is that, well, I could have a shape that I break into a bunch of lines if I know how to calculate the electric field from a line. Similarly, we're going to learn how to calculate the field from a ring, and then we can make a disk out of rings. So that's one technique to use here. You could imagine calculating the field from a cone out of a bunch of rings, for instance. Now then, this is again going to be something that you might want to draw a separate picture for, or you can draw it connected to this picture as long as this picture was big enough. These pictures have a lot of information in them, and it's really important that your labeling is clear. So don't be afraid to take up maybe half a page or a quarter of a page drawing these pictures. So you want to draw the electric field vector, and remember this is a vector, so it has magnitude and direction, for one or two small pieces of charge. So you're looking at a specific piece of charge, again we will go through an example, and then labeling what direction does the field point, and starting to then label all of the quantities. So you need to identify the distances and angles that are relevant, since the angle is going to influence the direction of your vector. So again, so far we haven't done any math yet, we've just been drawing pictures, but a big part of this is going to be setting up the geometry that you need to do the problem. So the second half then actually gets into the math. So the representation, so we have our picture, our representation, and now we're moving into math. And all we're doing is saying that our total field is the sum of the pieces. In many cases, we're going to need to do an integral, but not always. So you need to do your sum. So make sure that you're looking at components. These could be three-dimensional problems. You might have X, Y, and Z components. Frequently, mathematically, that's too hard for us to do in intro physics, so you're only going to have two components. But make it really clear what components you're working on. Make it really clear what your coordinate system is. Now, this is really the hard part, the second step here, is that ideally you've set up your sum and you've set up this initial equation, which might, for instance, just look like the field from point charges. And you have delta Q in that. You have a little bit of charge. But now, when we go to do the integral, we need to do a spatial integral. So we need to move to something like dx. Now, depending on what our shape is, this process is going to look different. So I can't tell you exactly what to do here because that is really the crux of the problem. So make sure that you are not just trying to directly integrate over your Q, but that you move into a spatial integral. And again, that's typically going to be along one dimension, so X, Y, or Z, depending on how you've defined your coordinates, or potentially an angle, though that's a little trickier, so be careful about doing angle integrals, since once you say something like d theta, you have to think about how that might be influencing other values. So then you want to express all angles and distances in terms of the coordinates, meaning whatever coordinate your dx is. So why that matters is that you might have a radial component that matters, and you might have a theta, and as you're changing your spatial coordinate as you do your integral, that the angle is changing and the distance is changing. So make sure that you express this, unless it's fixed, in terms of the coordinate you're doing the integral over. And when we talk about line of charge, it's a great example of this. The last step is to do the integral. You have a lot of thinking to do before you actually do the integration, and that includes setting the correct limits. So please be careful here. This is one of the places where calculus-based physics and algebra-based physics are really on different pages, in that there's mostly physics and geometry up here thinking about these. Then you have to make sure that your limits are correct, and then you do an integral. If the integral is appearing in the first half of your work, you have definitely made a mistake. The integral, this final integration step, should really be at the end. You might have a little bit of algebra to do after the integral itself to actually simplify. Lastly, you want to check your result, and this is going to be hard because frequently the answer is going to be complicated. And that's where we talked about those limiting cases earlier. So you can use a limiting case to actually think through whether your answer makes sense.